wanted to work through an example that involves a electrical charge arrangement. It involves a resulting electrical field. It involves the concept idea of electrical flux, and it utilizes Gauss's law, the flux law, that tells us the relationship between charge and electrical flux. It also uses some arguments of symmetry to help solve the problem. So in this problem, we're asked to imagine a long, straight wire. This long, straight wire is uniformly charged with charge Q. This long, straight wire has length L. And we're going to figure out the electrical field nearby the straight wire, close to the straight wire. Actually, I'm going to figure out the electrical field at a distance r radially from the long straight wire. And that distance r is going to be small to the length of the wire. And that's what I mean by nearby the wire. I've got a sketch here of the wire. That's the horizontal straight line. I've indicated the length of the wire. I have indicated the charge on the wire. Remember, this is spread uniformly along the length of the wire. And before starting any calculation of the electrical field, before starting any calculation of the electrical flux to find the electrical field, let me just make some sketches about what I know about the electrical field, and making sketches of a suitable surface to figure out the electrical flux. So I've just drawn in red a number of field lines that are meant to represent the electrical field, its direction and its strength along the length of the wire. And I want to say a few words about how I drew these field lines. So firstly, the wire is, I'm assuming it's positively charged. And so positive charge is the source of electrical flux, source of electrical field lines. And so the field lines are going to emerge from the wire. So my field lines are emerging from the wire. Above the wire, they're heading upwards. Below the wire, they're heading downwards. In both cases, they're emerging from the wire. You'll notice a couple of things about the way I drew the field lines. So I drew the field lines so that at least at distances where we're relatively close to the wire compared to the length of the wire, the field line, if you're above the wire, is going to be radially upwards. The field line, if you're below the wire, is just going to be radially downwards. But the field lines above the wire aren't going to point towards the left, point towards the right. And below, they're not going to point towards the left or point towards the right because the ends of the wire are far away. And in this region close to the wire, in the middle of the wire, there's nothing to cause the field lines to point left or right. The field lines are just going to point away from the wire, upwards or downwards, above or below the wire. So that was one thing that I incorporated in this picture. I also drew the field lines sort of regularly spaced, as if it's a uniform field. Again, if you're far from the end of the wire, then the field lines don't know about the ends of the wire. The field lines only know about the charge on the wire. And since the charge on the wire is uniformly distributed, the field lines along the length of the wire will be uniformly distributed. So this is the pattern of electrical field that is being produced by this wire. Now, we said we want to calculate the electrical field nearby the wire. And I'm going to pick a point that's nearby the wire. It's indicated here. It's indicated here by this radial distance r that this point is, this field point is from the wire. What I'm going to do is situate that field point where we want to know the field on an imaginary Gaussian surface. And that imaginary Gaussian surface is going to help us calculate the field at that point by allowing us to calculate the flux through that surface. And so to this picture, I'm going to add to the field point, the sketch of the field point, I'm going to add the Gaussian surface that's going to include that field point. So here's the Gaussian surface in magenta. It's a cylindrical closed surface. That means it has a cylindrical wall to it, and it has two end caps on it, one on the left and one on the right. Now, again, I'm thinking of a point that's close to the wire compared to the length of the wire. So the side walls of the cylinder are going to be much larger, much more area than the two little end caps, because R is much smaller than the length of the wire L. The cylindrical Gaussian surface I've centered on the wire. So the wire is the axis of the cylindrical Gaussian surface. I did this because this arrangement of a cylinder centered on the wire and the wire producing a cylindrically symmetric field allows me to exploit the symmetry, the cylindrical symmetry of the situation to calculate the flux through the Gaussian surface and thereby calculate the electrical field strength at the Gaussian surface. So I'm taking advantage of the fact that the wire has a cylindrical symmetry to it. You can walk around the wire at some radius and it always looks the same. That tells me that the field has a cylindrical symmetry to it. I can walk around the wire at a given distance and the field is always the same strength radially outwards, which allows me to use a Gaussian surface centered on the wire that's a cylinder to take advantage of that symmetry. So at this stage, I started with the arrangement of charge. I thought about what the field must look like. I thought about what Gaussian surface I want to use, calculating the flux. I'm now going to go on with a sort of more rigorous mathematical part of the solution to find the field by calculating the flux, by using the flux law, by using Gauss's law. So let me write down the flux law. Remember, the flux law tells us that the flux through a closed surface, my Gaussian cylindrical magenta surface is a closed surface, is in proportion to the charge inside the closed surface. This is the charge on the wire that's enclosed by the closed surface. And there's a proportionality constant, and it's 4 pi times the Coulomb constant, or it could be division by the electric permeability, epsilon naught. So this is the flux law. This is Gauss's law. And what I'm going to do is on the right-hand side, I've got the charge, and just leave that alone. On the left-hand side, I've got the flux. I'm going to fill in the details of the flux through this particular surface from our definition, our concept of flux. So the flux is going to be equal to the strength of the electrical field. I'll just write it as E, but recognizing that this is just the size, strength, magnitude of the electrical field. The size of the Gaussian surface, I'm just going to write that as A, but again, recognizing that this A is the just the size of the cross-section of the closed Gaussian surface, times the angle between the field vector and the A vector, area vector that represent the surface. And that's going to be equal to 4 pi k q. So that's just filling in the general definition of electrical flux. When you've got a surface, it's immersed in an electrical field. The field is uniform over the surface, and this equation gives you the flux through the surface. Now, I can tailor this equation on the left to my particular surface. So I'm going to go ahead and do that. I'm going to write it down, and then I'm going to describe it. So firstly, the area of the surface. the area of the Gaussian surface is the area of this cylinder. So the side walls of the cylinder, well, in cross-section, they're a circle. The circumference of a circle is 2 pi r. They have a length, the side walls, of L. So actually, imagine unrolling the cylinder into a flat sheet. Its height would be the circumference of the circle, 2 pi r. Its width would be the length of the wire or the Gaussian surface, L. And so the total area of the side walls of the surface is 2 pi r times L. And that's the quantity I've written down in parentheses here. The electrical field passes through that surface. The electrical field, if you're on the top of the cylinder, is passing through that surface upwards, which would be in the same direction as the vector A, representing that part of the surface. If you're on the bottom of the surface, the electrical field is projecting downwards, which is in the same direction as the vector A on the bottom of the surface. That too is downwards. If you're at the front, E and A, those two vectors, are outwards, away from the page. If you're at the back, then E and A, the two vectors, are again in the same direction into the page. Everywhere over the cylindrical wall of the surface, there is an electrical field. There is a area vector that are parallel to one another. So the angle theta between E and A, everywhere over the side walls, is actually 0 degrees, and the cosine of 0 degrees is 1. That's where this 1 came from. Now, there's one other thing that I hid in this little equation here, in this last step in these equations here. That has to do with the end walls. You know, there are end walls, end caps on the cylinder. We have to have a closed surface. So haven't I just missed out the field of the end walls, in particular, the flux through the end walls? Well, the answer is actually no. The field lines were coming radially outwards. Above the wire, they go up. Below the wire, they go down. They don't go left or right. And so there's no field lines punching through the left-hand end cut, punching through the right-hand end cut. And so there's no flux through the left and right-hand end cups. I'm safe to ignore that because it has no contribution to the total flux through the surface. And so this equation is good. I can safely ignore the end caps. If you look at that equation, I can cancel out a 2 pi on the left-hand side with a 2 pi on the right-hand side, leave a 2 over here. I can divide through by R and L. And if I do that, that gives me an equation for the electrical field at the surface of the Gaussian surface at a distance R from the wire. And that's what I wanted to figure out. So if I go ahead and do that, I'm going to get on the right-hand side 2K times, these are features of the wire, the charge on the wire and the length of the wire, times Q over L, divided by the distance from the wire. And that distance from the wire, radial distance from the wire, is R. So that is a solution to the problem of what is the electrical field nearby a long straight wire that's uniformly charged, has charge Q, has length L. It's given by E equals a constant, it's 2K, times the charge divided by the length of the wire, which is what we would call the charge density on the wire, the linear charge density on the wire. It's the coulombs per meter on the wire. It depends on the wire, divided by your distance from the wire, this radial distance R from the wire. It says that as you walk further from the wire, then the field goes down, and it goes down in inverse proportion to your distance. So if you walk twice as far away, the field will get 1/2 the strength. If you walk 3 times as far away, the field will get decreased to 1/3 of the original field. Notice that that's different from what we met in Coulomb's law. There, the field is proportional to the square of the distance from the charge. It's different from what we met with an electrical dipole. There, the field was in proportion to 1/3 the cube of your distance from the dipole. Here, the field is falling off as just 1 over r, just in proportion to the inverse of the distance. So that's one interesting feature. Another interesting feature is that the field nearby the wire, it's not simply determined by the charge on the wire. What it's really determined by is the charge per unit length on the wire. If you pack more charge per centimeter, you'll get a stronger field. If you pack less charge per centimeter, we get a weaker field. And so that's the dependence on Q over L, not just on Q, but Q over L, the linear charge density. Anyway, I wanted to work through that an example. It's an example of charge, of field, of flux. It's an example of utilizing the flux law, utilizing Gauss's law, a difficult problem with Coulomb's law. It's an example where we had to augment laws of physics like the flux law, like Gauss's law, with some arguments about symmetry, arguments about patterns. You know, if you have a long straight wire, then nearby the wire, the field's going to be radial. That's kind of symmetry argument. If you have a radial field and you want to explore that field, we're going to use a cylindrical Gaussian surface. That's a symmetry argument.